differential equations play a big role in the development of many useful inventions in our daily lives. We see its applications everywhere around us, but we just do not recognize them. I'm Baron, a mechanical engineering student, and today I'll be elaborating further on how ordinary differential equations is applied in the automotive industry. Firstly, what is an ordinary differential equation and why do we need to solve them? An ordinary differential equation, or ODE, is an equation with an unknown, complex or real variable x and its derivatives with a function of x. The unknown function is generally represented by a variable, often notation y, which is based on x. Therefore, x is mostly called the independent variable of the equation. We usually use the term ordinary to contrast with the term partial differential equation, which may be respect to more than one independent variable. The objective of solving a differential equation is to find the unknown function, known as the particular solution of the differential equation. This can be in the form of different orders, such as the first order, which is deriving the equation once, second order, deriving the equation twice, and so on. In the automotive industries, ODEs are used in the manufacturing of engines and bodies of commercial vehicles, which include the brakes. The brakes are used to absorb energy from the moving vehicle to slow down the vehicle. The function of the braking system is to stop the automobile in the shortest possible time by converting kinetic energy of the vehicle into heat energy, then released into the surroundings. The motion of a body is described by its position and velocity as time changes. This is also known as the law of inertia in Newton's second law of motion. Disc brakes are the most common type of braking systems in cars and buses. It consists of a brake rotor which is directly attached to the wheel. When the vehicle is required to come to a halt, friction is applied to the gears and brake pads. ODEs are applied to find out the duration taken till a vehicle stops or meets another object. Next, let's look at a real-life example. A Ferrari weighs 1,500 kilograms and is moving at 64 meters per second. If the brakes provide 6,000 newtons of friction force, how long would it travel before it stops? Firstly, we can form an equation as follows. The equation form is basically force equals to mass times acceleration, where acceleration is the second derivative of the position, and we can write it as x double prime. It is also given that the velocity, or x prime, at the origin is 64 meters per second. Simplifying the equation, we will get x double prime equals to negative 4 meters per second square. Take note that it is negative due to the force acting in the opposite direction to the movement of the car. To get x prime, we need to integrate x double prime. Integrating both sides, we will get negative 4t plus c1. To verify c1, we know that the initial condition at x prime t equals to 0 is 64. Thus, subbing into the equation, we will get c1 equals to 64. This is the speed that the car is traveling at each moment. We need to find x, so we integrate again. Integrating x prime in terms of t, we get negative 2t square plus 64t plus c2. Subbing in x0 equals to 0, thus c2 equals to 0. We get the general solution of x in terms of t to be negative 2t square plus 64t. To find the stopping time, x prime t equals to 0, or negative 4t plus 64 equals to 0. 64 equals to 4t, and thus t equals to 16. Finally, substitute t equals to 16 into the equation x in terms of t equals to -2 multiplied by 16 squared plus 64 multiplied by 16, and the solution will be 512 meters. To support and assist in the various braking systems of an automobile, suspensions are connected to the system. A collection shock absorbers help keep the wheels in contact with the surface and provides a cushion for the rider from bumps and holes. This work proposes to control the normal forces using linear motion law exerted by the wheels on the road. It is the vertical acceleration of the axle in a short time which creates these normal forces during braking phase. It also maintains the center of gravity of the vehicle to maintain stability on all corners and prevents damages to the vehicle while braking. As we have learned, motion isn't perpetual. This means that there will always be resistance acting on the automobile, no matter how big or small it is. With a damped system, the mass now has two opposing forces. Firstly, the force of the spring equals to -ky, and secondly, the force of a fluid equals to -cy prime. Again, by Newton's second law, the resultant force is equals to ma. Expressing acceleration as the second time derivatives of displacement, we can rearrange the equation into a second order homogeneous linear ODE, m double y prime plus cy prime plus ky equals to 0. Simplifying this equation by dividing m, we get y double prime plus c over my prime plus k over my equals to 0. The characteristic equation of 2 is r square plus c over mr plus k over m equals to 0. Substituting these variables from 3 into the quadratic formula, we get -c over 2m plus minus 1 over 2m multiplied the square root of c square minus 4mk. Does the term inside the square root look familiar? That's right. This is the term used to find the roots of homogeneous second order ODEs and their solutions, where the behavior of the solution will depend on the value of the discriminant. With this equation, you can find out how the vehicle body will move up and down when the vehicle is driving at a certain speed on a bumpy road, and the vehicle body is also subjected to vibration. Let me show you how we solve a real-life suspension system mathematically. A bus with 500 kg mass at each corner has a spring constant K of 2000 newtons per meter, with a damping constant of 1000 newtons second per meter. The bus drives off a curb of 15 centimeters height with an initial velocity of 0 meter per second. Substituting these values for m, we get y double prime plus 2y prime plus 4y equals to 0. Characteristic equation is r square plus 2r plus 4 equals to 0, and the roots are -1 plus minus square root 3i. Therefore, c square is larger than 4mk, which means overdamping occurs. As we have complex conjugate roots, the general solution to equation 4 is y in terms of t equals to e power -t in brackets a cos multiplied square root 3 times t plus b sine multiplied square root 3 times t. Let's find a particular solution of 6 by applying the initial conditions. First, we apply the initial displacement condition and we get a equals to 0.15. The first derivative of 6 is, we can now apply the initial velocity to equation 7 and we get square root 3 multiplied d equals to 0.15. Therefore, d equals to 0.15 over square root 3. Thus, the particular solution for this example is